Okay then, so I'm just going to run through how we would code up the bathroom model. So the first thing I'm going to do is save the file I'm in. So I'm going to just say this, call this getting started. So this is a text file, and I'm going to save it in a folder that I've called bathtub model. Save. Now what's nice to do is add that folder into my file browser here. So if I right click here, I can go add top level path, and if I go this, I've now got my my folder here which can have all my files in. And here you see filter, so if this is only on Python, it's only going to show me the Python files, but if I've got data files, it's good to set this to all files. Right, so here's my getting started. So what do I want to do here? Define the problem. So we have 4 bathtubs, and let's call this A, B, C, and D. And whenever I'm going to call a variable, I'm going to try and use something that's MATLAB compatible. So for instance, if we were talking about the concentration of a chemical in A, we'd use square brackets when we're writing it out, but that's not allowed in Python. So for this case, if it was a concentration, I might call it CA, or if it's a volume of liquid, I might call it VA. Right, so each holding a volume of water, call that VA, VB, VC, VD. Right then, system starts at time t equals 0. A is full, all others empty. Plugs removed, so water can flow A to B to C to D. D keeps its plug. The water accumulates. Right. So we've got 4 bathtubs stacked, so the water from bathtub A flows to bathtub B, then to C, then to D, where it accumulates. What does it say? Water flows. Right, so want to model this. Python. The stage 1, write down reactions and their rates. So we're going to assume that the rate of flow out the bathtub is proportional to the volume of water in the bathtub, and this is just our first model. We might go on to edit that, but let's build the model assuming this happens. So we've got reaction 1, which is A flows into B, and the rate of this, let's call that rate, is RAB equals K1, where it's proportional to the amount of water in A, so we call it equals to K1, where that's a constant of proportionality, times the volume of A, so VA. So we'll write it as if we're going to code it. We've got that. Then we've got the similar reactions, B to C, C to D, and we're going to assume that our bathtubs might have different size plug holes, so the rates so the rate at which it flows out might be different, so we'll have K2 times the volume of B times 3 times the volume of C. So we've written out our reactions and the rates of those reactions. Okay, reaction 1, reaction 2, reaction 3, or process 1, 2 and 3. So maybe I'll call this processes. And so the next thing is to note that conservation of water means flow out of A equals flow into B, and the same for the other tubs. Flow out of B equals the flow into C. Flow out of C equals the flow into D. So the water can't go anywhere else but in the bathtubs. And what we might add there is equals RAB equals RBC equals RCD. So there are rates for the flow. So if we now want to write down rate of change in each tub, so the rate of change of water in each tub, so we're talking about D, the rate of change of the volume of water in A with time, which we're just going to call equals RA. So the rate of change of A equals the rate of flow into A minus the rate of flow out of A. Okay, and that's the same for each bathtub. Then we've got A, B, C, D, B, C, D. Now what we know is the rate of flow into A is 0 because that's at the top of the chain, and the rate of flow out of A is this right here, equals this. So we can do this for all of them. So the rate of flow into B is this rate of process AB, or the flow of A between A and B. And we have the flow out of B, we've got to subtract that. So the net change is the flow in minus the flow out. So we'll repeat that here. RBC minus RCD equals, so the rate of flow into D is RCD, and because the plug's in, there's no flow out. So let's neaten that up. So these are our rate equations, and because we've actually put values on these rates, we can rewrite that here. So equals, 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 equals. Sorry, this is 0 minus that rate, so we've just got minus that rate. So let's say minus 1 times. Then we've got RAB, that's just this one, minus K2 times RBC. Just carry this on, minus, if I were to align these up, instead of that, I'm just going to put the naught minus, which makes it a bit clearer, I think. So minus this. Oops. That should be VB. VB. So it's proportional to the volume in B, not anything else. So K3 times VC, and finally we have the flow in K3 times VC minus 0 because there's no flow out. Right. So these are the equations that we're interested in, and in particular when we get to Python, I'm going to just keep the bits that we need to use in our code. So this is the rate of change of D. Let's keep only keep our final bit. So when we come to this is d by dt expressed in Python. Okay, so at any stage, given the volume in A, volume in B, volume in C, and we don't actually use the volume in D for this calculation, we can give you the rate of change of A, the rate of change of B, the rate of change of C, and the rate of change of D.